So in terms of using the language, you can, at this hackathon, you can use it in several different ways. In the world at large, if you just go to the wolfram.com website and you press the button that says Development Platform, you will get into a free, you don't even have to log in, cloud version of everything that I'm going to show you here today. I'll actually use the desktop version of our development environment because it's a little bit smoother and faster, because it doesn't have to do a bunch of web transactions to do things. At this hackathon, you can also download the Wolfram desktop that allows you to do that too. In terms of one of the things that's been interesting to us recently with Wolfram language is we've reached the point where we've sort of automated enough of what has to be done that kind of the fancy R&D folk who've used Wolfram language in Mathematica for many years in the past sort of don't have much advantage over the kids who've never done programming before in terms of actually getting programs built. And so one of the things we've done a lot of recently is building things for programming education, and there's a thing called Programming Lab. So this is it doesn't look like there are very many people who are in the never programmed before category. You never know what to expect, but this looks like definitely a hardened programmer crowd here. If there are people here who are in the never programmed before category, you might like this Wolfram Programming Lab, which kind of starts from nothing and gets to fairly sophisticated programming kinds of things. And I was going to show you. So one of the things that I did recently is to write a book that you can find free online, and you can also find a physical copy, which I was about to hold up here, but I realized I don't have one. But there's one over at that table over there. This is an introductory book about Wolfram language for people who haven't programmed before, although somewhat to my surprise, it also seems to be being read by very sophisticated people, and it's a quick read as an introduction to the language. Okay, well, so let's actually do some things. Let me start off just giving you a very quick sort of run through of sort of things that the Wolfram language does, and then you could see I was just starting to pull in some NASA-related data here, but I didn't actually pull it in yet. But let's start off with some basics here. So the basic form of interaction with Wolfram language that is most convenient for developing things is you type in a piece of code, it types back the result of evaluating that code. So, I could type in some computation here, and I'll get back the results of the computation. I could say, make me a 3D plot of, some, I don't know what, some funny thing here. And I'll get my 3D plot, and I could say, once I have this plot, I could export it in all kinds of forms. I could do all kinds of things with it. There's the plot. Let me give it a parameter here. Let's say I put a parameter A there. I can make a user interface here. And I'll show you how to take all these things that I'm doing and deploy them on the web and so on, if that's what you want to do. But here I'm just making a manipulate where I can just vary that parameter and get the result. And this is kind of standard Wolfram language stuff. So kind of the idea of Wolfram language is be able to deal with sort of any kind of data. So a typical type of thing we might do is let's pick up an image here. Let's say we get the current image. Let's get another current image. Okay, there's a current image. Now we can take that image and start doing some kind of image processing. So let's say we want to edge detect that image. Okay, there's the result of edge detecting that image. If we wanted to, we could dynamically, edge detect our current image, let's go ahead and do that, and then we get that thing working in real time. We could also do something where we take, this is so we can do all sorts of image processing. We'll probably do a bunch of that with interesting astronomical data and so on in a little while here, but I just want to kind of run through a few basic things we can do here. We can deal with, I don't know, let's say we want to deal with graphs. We could say make a random graph, 100 nodes, 200 edges, there's the graph. We can go and do something like make a plot of communities in that graph, let's say. We can do that from data, whatever else we want to do. We could, let's see, what other kinds of things can we do? We might take, let's start looking at some kind of real-world data. So an important feature of the language is that it knows stuff about the real world. So for example, let's say I type in New York City. Okay, New York City is just an entity in this language. thing I should explain about the language is that it's a symbolic language. So when I type in X, in most languages it would say, what is X? I don't know what X is, I'm confused, it's an error. In Wolfram language, X just stands for X. So you can do things, I could say, perfectly well say, just nest the function f symbolically, starting with X. I could as well here, I could take, let's do this, let's take that picture there, and I could say something like, let's take that, let's nest it. Okay, there's the nested f of that picture. Perhaps a more interesting thing, why don't I do the edge detection? So this will now make nested edge detection of that picture. So this is essentially iterating edge detection on that picture. For example, let's combine some things together here just for fun. Let's say we want to just take, let's take the n-way nested edge detection of this picture, and let's make a manipulate out of those, where we're saying, let's manipulate that, let's say n from 1 to 20 in steps of 1 or something. So now we should get a control there, and as we move this control, I've never actually tried doing this before, but we should get, yeah, there we go. We get this kind of successive nesting of those kinds of things. Actually, I have another idea, something we can do with this. Let's get those, let's take those things, and let's take the nested versions of that, and let's take that, let's say it's 10 times nested here. Okay, let's do this, and actually, you know what I'm going to do? I'm going to image resize this image so that I make a lower resolution version of this image. So let's make a 200 by 200 version, pixel version of that image. Okay, so there we have that. Now, my idea is, which may or may not work, let's try making an image 3D out of this. Let's see what that does. Oh, that's bad. Okay, that means should be an array of rank with machine size numbers. Oh, consistent color space. Okay, so what I could do here, I could say image conform, or I could just be lazy and I could drop the first of these images. Let's just drop, let's see, that was line 2, so let's just drop the first of those images, and now hopefully I can say image 3D if that percent means the current thing. There we go, that's cool. Okay, so there we have a 3D image that's made from the stack of successive nestings of that 2D image. And we could go ahead and do image processing on that 3D image if we wanted to as well. But I digress. We were talking about, we were looking at New York City, for example. So we should be able to, where is this? Okay. Let's start looking, well, let's see, where does it think we are? Okay, that's a geoposition. Let's find out, let's actually geo-identify, let's say city, and then let's say here, and that will tell us, that will hopefully tell us which city. Oh, well, I don't know where that position is. Let's find out where that position is. Let's say geographics. Let's make a disk. Let's make a 10-mile diameter disk around where we are right now. So let's say 10 miles here, and let's see where it thinks. I mean, this is based on, very interesting. Okay, this is where it thinks based on GeoIP of this computer. This is where it thinks this computer is right now. So I think we have to, let's see, let's just find out where on earth it is. I don't know, I have no idea. Oh, wow, that's exciting. Oh, it's in Kansas. Right. So that's probably, I bet that position is actually the center of the US. So let's find out. So let us find out what's the geographic center. Let's see what happens if I do this. I think that will probably, oh no, that doesn't work. Okay, let's try this. I'll tell you what, actually the easy way to do this, the cheap way to do this is to say center of the US. And okay, there's the center coordinates of the US, and it's 38 minus 97. So it looks like we are, wherever it thinks we are based on this computer, it's really close to the center of the US. So let's see what, let's see if we can actually work out. Let's take the center of the US according to this. Okay, there's here. Let's just find out the geodistance between here and the center of the US. Okay. Okay, so it thinks right now, for whatever crazy reason, it thinks this computer is 48 miles from the geographic center of the US. Who knows why? In any case, I've already started showing you some of the kinds of things that we can do. Let's say we take New York City, and we could say, something like, what's the population of New York City? This is data that we've curated and so on, has that kind of information. So we can, let's try doing something a little bit more astronomical. Let's say we take planets, do this for exoplanets or all kinds of other things as well, but let's just take planets, and let's say, let's just get a list of planets. Okay, there's a list of planets. So now let's say we want to get, let's say we want to say the value of the mass for each of those planets, okay? So there's the masses of all the planets. Now we could take, for example, I don't know, what would we want to do there? We could take, well, we could just take the total of all those masses. Actually, we could take the total of all those masses and divide it by the mass of the sun. I don't know what this, see what we get there. Okay, so the masses, so that just tells us what fraction of the mass of the solar system is in planets versus, well, the sum of the masses of the planets divided by the sun. So let's try doing something else here. Let's take those, let's take the planets there, and let's go ahead, where were they, line 16, and let's go ahead and get images of all those planets. And so one thing we might do is make some kind of image collage where we say, let's make a collage where the size of each planet is proportional to its mass. So that's easy to do. We just say image collage of line 17, arrow line 20 there, and we should be able to get a plot that shows the planets in with sizes proportional to their mass. So we can go ahead and do we can do all kinds of things here. Maybe we could take let's do something different. Let's do something to do with let's say satellites. So we could say, for example, let's take something like the ISS. So we can probably say, let's try seeing what happens if we say, let's try this. Let's see if this works. I'm not sure if this will work. Let's see. So we're asking it to work out, yeah, it did, okay. So that's asking it to work out the geoposition of the ISS. So that will give us the lat long and then the vertical, whoops, that was a bad idea. The vertical position of the ISS. So actually what we could now say is, let's say geovisible region and then this position of the ISS here. So let's take the geoposition of the ISS, and then we can say, let's make a map where we show on geographics, oops, we show on what am I typing? Geographics, I show the geovisible region of the ISS. So that's showing now a circle that shows what points on the Earth are visible to the ISS right now, maybe I can show this. Let's just do this for. Let's just show it for a. Let's go ahead and show this for geo range. Why am I typing that suddenly? Geo range all. So that will now show us where the ISS is on the Earth. If I wanted to, I could show a different map projection. So I could say something like geo projection, arrow. I don't know. Anybody got a favorite? We've got hundreds of these map projections. Let's do Lambert azimuthal, for example. So there's where the ISS is right now. Was when I typed in that that line. Actually, it might be fun to see what the. Let's just do this. Let's type that same input again, and let's see whether it's different. And let's see that. Okay, so that's now the new. No, that looks like it's the same position. It obviously got itself cached. Let's see how we would solve that problem. That's an interesting problem. It might have cached the position, thinking that geopositions. I think that's a bug. I think it cached the position because it thinks things don't move in geoposition, and it doesn't know about satellites. Okay, that's good. Well, I'm sure we can ask it the actual position at a particular time, but let's not worry about that right now. Let's instead try. What can we do? We could try getting some other satellites. If somebody has some favorite satellites, we could probably try getting some of those. We might say random entity, let's say satellite here. Let's just take 20 random satellites. Okay, there they are. I don't know what these are, but let's see whether they're. Let's try taking the geopositions of those 20 random satellites. Let's see what many unable to obtain location information for Sputnik 25. I doubt Sputnik 25 is among us anymore. Okay, well, so look at this. Cosmos, yeah, I mean, Luna 11 is probably not. Actually, let's find out whether we actually do have interesting properties of something like Luna 11. Let's see whether we have. we might have the position. Let's see what happens if I say geoposition of Luna 11. I don't know what Luna 11 was. Maybe somebody here knows what it was. Oh, sorry, it doesn't know where it is. But let's say, I mean, if we want to take something like, Apollo 11 landing site, let's see what it does with that. So that should give us so that gives us a geoposition, but now that geoposition is not on the Earth, but on the Moon. And if we say geographics of that, georange to all, it should, if everything's working correctly, be a plot. Yeah, that's a good sign. Okay, that's a plot. Actually, what I should have done here is I should have said geo list plot, and that would plot this. Let's do this. Let's take, let's say, Apollo moon landings, and that should be, let's see what those are. Let's try an entity list of those. Okay, so those are the various Apollos that landed on the moon. So now let's go ahead and say there seems to be a property here, lunar landing location. So, oops, let's say, okay, hold on. That I want to take, yeah, okay. So let's do this. Let's say, let's get the, let us go ahead and say, I want the entity value of that with line 36 with a lunar landing location. Let's see what happens here. Oops, I obviously asked for the wrong thing. Okay, hold on. When in doubt, I could always look at the documentation, but let's avoid that for a second. Let's say we want to do, let's just say we just look for properties of this. Well, actually, I'll tell you what, I could just say lunar landing date. Okay, landing, launch site, landing position. There we go, that's what it is. Okay, so what I want to do is say, for this, for line 36, I want to get the positions on the moon where all of those things landed. And now I could say, for example, I could say something like geo list plot of those. Oops, I need to say invalid map style, no street map labels for the moon. So I have to tell it geo range arrow moon. And what I should be able to get here, let's do this. Let's say, I want to ask it to show me that. Okay, so what this should be doing, no, that's foolish. Okay, let's see. I think I need to do, geo background arrow. Let's try that. Okay, that wasn't very exciting. That was showing no background. That was showing the positions of the lunar landing sites, but without a background image of the moon. Let's see what happens if I just say automatic. Oh, there we go. Okay, so those are the positions, those are the landing sites on the moon. And one thing we could work out, just for fun, I'm digressing here, but I think this is, I'm having fun at least. So we could get, for example, I could get a traveling salesman tour going if you wanted to, like visit all of the lunar landing sites. So let's try. Let's say this is okay. So that's line. Okay, so sites, landing sites is line 39 here, and now I could say find shortest tour of line 39, and so that should give me. So okay, so 2,500 miles. You can make a tour of all the lunar landing sites. So now what I should be able to do is take those. And I should be able to take those, and I should be able to say this. I'm going to reorder them this way. I'm going to say, let's see, joined to true, and maybe I want to say, let's make it geo-range all, which should show the whole moon. And okay, there we go. So that's the traveling salesman tour of all the landing sites for the Apollo missions. I think it's cool we can do this stuff this easy. All right, well, let's try doing, I want to show one more thing, and then we're going to dive into actual NASA data. The thing I wanted to show, I mean, sort of the idea of Wolfram language, as I was explaining, is sort of automate as much as possible. So there are many different sort of kinds of things that have been automated, whether it's visualization techniques or image processing or computational geometry, all sorts of other things like that, or all of these kinds of things with data. But an important area of automation these days is machine learning, and we've got pretty good ways of doing things like automated classification and things like this. Actually, for example, let me show you an interesting case here. So if I say image identify, here, let me see if I can do something here. Let me see if this works. This may not work from here. But if I say web image search, let's try something silly. Well, all right, let's try something silly to begin with. Can't resolve host name, that's a bad sign. Okay, it might have worked. Okay, so let's say, let's see, I want all, 2. Okay, so this purports to be weird. Okay, this is actually going to be a bad example. So let me first pick a better example. Let's pick a, I don't know. Let's pick a type of animal. Okay, let's make it simple. And you got a favorite kind of animal? Okay, there's an otter. So these are just, I mean, if we, in Wolfram language, we will certainly know about otters, so we can just say an otter, okay, there's a type of thing. We could say, give me an image of the otter. Okay, there's a sort of standard image of an otter. But here I just picked otters off the web, so I'm just saying, here's a bunch of otters on the web, and now we've got an image identification function which can take one of those pictures of an otter here, and we could say image identify and give it that picture, and now it will say it's an otter, okay, a certain type of otter. Now I could, for example, let's just take that function, image identify. This was line 53, and I could just say image identify. Let's say map that over line 53. So what this is now going to do is it's going to tell me for each of those pictures what it thinks it is. And maybe I could tell it to make. It wasn't very exciting here, but I could make that wasn't a very exciting word cloud, but I could make a word cloud of what it says it is. Let's say, just for fun, we'll just try it because it's kind of going to kill the thing. I wonder what happens if I say that. Will that work? No, that doesn't work. Okay, so this is going to give me pictures of things that are supposed to be Martians. Let's do. I think it's mostly the movie. Yeah, mostly the movie. That's it. So let's just see what happens. It'll probably do stupid things here, but let's tell it to image identify those. Okay, person, vertebrate. Okay, that's not so bad. Let's actually just for the hell of it, let's actually try making this in such a way that we can see what it's doing. So let's make a column where the top of the column is so this hash thing is making a pure function lambda expression. This hash thing represents the thing that's going in. So let's say line 59 there. So this is now going to make something where everything is going to be labeled with, okay, person, good, vertebrate, okay, not so bad, it's not obviously wrong. Person, great, and hill, okay, not so bad. Actually, what's kind of interesting to see, let's take that one, for instance, and let's dig a little bit deeper. Let's say we say image identify of this in all categories, and let's show the first 10 of them, and let's show probabilities. I think I got this right. Let's see whether that works. So what this should do, yeah, there we go. So that's showing us the probabilities. Okay, so there's a 0.1% probability that it's a rock squirrel, which is a little bit obscure, but that's what it has to make a trade-off between specificity and certainty. It's pretty sure it's a vertebrate. It's a little less sure it's a mammal. It thinks it might be a carnivorous mammal. And it's giving those things with certain probabilities. Actually, we could probably make a more interesting word cloud. This would be more fun. Let's take those things on line 62. There's the word cloud of what it thought that picture might be. Actually, why don't we just for fun, let's let it go all the way down. Let's say all here, and it'll probably generate a huge long list. Maybe it'll be too long a list. Let's see. Oh, come on. That was maybe a mistake. I was going to get it to generate the list of all possible things it could imagine that this picture might be, which might be a super long list. I think it is a super long list, and I think this is a bad idea. Okay, never mind that. Let's get it to at least show us like 30 of those things. Okay, there we go. So now let's make a word cloud out of those things just for fun. Okay, so there's the the meerkat is down there, and the eared seal is down there at smaller values. Okay, so that's a little bit about what Wolfram language can do. So let's do something with some NASA data. So I had just started looking at the catalog of NASA data. Let me try and pull up what I had, and I was just starting at the very beginning there. Somewhere up here, I was just starting. I just downloaded a. I'll tell you what. Let me actually get more organized because we have this very nice concept of notebooks, and this document that I have here is a notebook. So let me actually make a section heading. And if I wasn't rushing so much, I would have been doing this all the way along. Meteorite data. So this was data about. We've got initial setup here. This is the way I actually like to work. Is put in all these notebook elements, and I could, close up that section if I want to. But anyway, I've got meteorite data here, so I've just been putting something in Dropbox here. Let's see what I have there. Okay, great. Let me go ahead and import the data associated with the satellite landings data set. And now let's, meteorite landings, what I'm talking about. And now I think, so this is now, now we're dealing with a jungle, so to speak, out there, because this is just some random data set that I'm seeing. So there's obviously some character encoding there, problem there, but let's not worry about it. Let's say, if I say the second element of this data set, we should get, okay, we'll get a bunch of things there. All right, so let's go ahead and, I'm sorry. Before I do this, before I launch into this, I've got another important thing I should show you, which is when you build something in this IDE interactively, how do you deploy this on the web? Okay, so let's show a little bit about how you do web deployment. So the way you do it is it's another kind of way of using symbolic things. So let's say we have a what can we do? Well, let's do just the animal example here. So let's say we have a we're going to make a form. It's going to have a field. The field is going to be called animal. What's expected in that field is the natural language input for an animal. Okay? And then what we're going to do is we're going to take that animal and we're going to say, I want an image of that animal. And let's say, for example, we want to magnify that image just because it might be too small otherwise. And let's say we do that. Let's say we're going to put it out on the web as a PNG. And now let me go ahead and let's say cloud deploy that. And let's say I want to make it so that this is something that's just available to the whole world. So I want to make this a public cloud deployment. Okay, so I'm going to take this, and now I'll get an object in our cloud. I can go to that object, and I can type, for example, meerkat or something in here. And this is now a smart field which understands natural language using the same technology stack that we use for Wolfram Alpha. And now I get a picture of a meerkat there. So now let's say I want to go back, I want to change my meerkat, I want to make it a picture. Let's just imagine that I want to do both the thing and the edge detection of the thing next to each other, okay? So just for something random to do here. So let's do that. So I just changed that code. Now I redeploy that API, and now let's put in a tiger, for example, here. And now what we should get is the tiger and the edge detection of the tiger, okay? So we just made, so now this thing that I just made, this little app that I just made, will also show up on the mobile, Wolfram Cloud mobile app. So it will be a little mobile app on Android. You can have it be a standalone APK file that you produce. There will be a standalone app that just is that particular form. Now I could, for example, I could go ahead and I could add something back to this form. I could say, for example, here, I could put in some number. Let's say I could say, depth or something here, and I could say that's an integer. Now I could say let's edge detect by that depth, and now I'll have a different form there which has a second field which asks for the depth and so on. And I can make arbitrarily complicated forms. I can make all kinds of different controls here. I could make something, I could make the depth be a slider, all kinds of other things like that. Now I can also take this thing, and instead of making it be a form like this, I can make it into an API. And so now this is a web API that I just created. That particular web API is just going to give an error because I didn't give it the parameters. So I could say question mark animal equals lion, ampersand depth equals 8 or something. And now when I run that API, I'll get, oops, I made a mistake here, but oh, maybe I didn't, I'm not sure what I did wrong here. But anyway, the idea is that I'm going into that, I'm calling this API from the web here. And now, let's see. Okay, oh, I know what I did wrong. Okay, in any case, if I wanted to, I could turn this API, I could say, give me embed code to embed that API in a Java program, for example. And so now this will generate the code that I need to call that API in our cloud from a Java program. And that's available for most common programming languages and so on. So that's some idea about how you can deploy things to the cloud. You can also deploy interactive things. So I could take, I don't know, I think I had something way up here where I had an interactive, let's take this thing here on line 8. Let's just cloud deploy that interactive manipulate. So now we can say cloud deploy of this, and can take that, and this should, oh, I should have made it public. Let me just make it public here. Let's say permissions to public. Okay, so now this will deploy that thing, that interactive thing. I hope it will deploy that interactive thing. Wake up, wake up. There we go. Okay, so it's deployed that interactive thing to the cloud, and it won't be as zippy as it was on the desktop, but we can still go ahead and do things with this in the cloud. Okay, so that was, and you can embed this interactive thing in whatever website or whatever else you want. Okay, all right, let's get down to business here. Let's do something with some NASA data. That was what I kind of intended to do here. Okay, where are we? Oops. Okay, so I have this meteorite data. Okay, so I just imported the meteorite data, and this is the general form of that data. It's kind of a mess, but let's. Okay, this was probably a date here. Okay, let me start showing you what we would do to do something with this data. Okay, all right. So let's take. So it looks like we've got the top of the first element in the data is a header. And then there's a bunch of kind of structured data underneath it. So I think what we probably want to do, he says, is to say, I'm gonna try this, because I want to thread that. Let's find out how much data there is here. Let's just see whether I can. I'm going to do something kind of in a stupid way. Okay, there's 45,000 lines of data here. Do I really want to do it this way? Let's see what happens if I just say, I'm just going to try this out. Let's just see, I'm going to test something out, just see whether I know what I'm talking about here. So I'm going to take the first 2 lines of data from that file, and I am going to, no, that didn't work the way I would like it to work, but this will, I think. So what this is going to do is it's going to make this into what's called an association, which is a associative array. Okay, so now what this is going to do, so what I want to do here is I want to say, take this for all the data in that thing, and I'll say, let's see, data set equals, and now I'm going to live really dangerously, I'm going to do it all in one go, and say rest of mdata, and came back quickly, that's a good sign. Let's see what happens if I display it. Okay, that's cool. Okay, so this is a data set that is that data that we just got from that file. Okay, so let's first of all, let's just for fun, let's find out, let's look at the mass field. Okay, so that's, what does it say? It's mass G, so let's say data set, and then let's say all, comma, and then mass of G. Okay, so that will give us 45,000 mass values. So let's go ahead and just make a histogram. We should be able to just make a histogram of those mass values. And something funky is happening here. Let's see. I'm suspicious here. Okay, let's stop that. Let's just get that list of mass values. I am suspicious that there's something wild and woolly down there. Oh, maybe not. Okay, let's just try this. I wonder why that's taking anything more than a microsecond to do. There must be something weird happening here. Let's look at the following. Okay, there we go. Okay, so there's the histogram of masses of of meteorites that are in this database. Maybe it would be more interesting if we showed, let's see, what would be a better example here? Maybe we should show the log, some kind of log histogram. Well, for that, I have to go look at documentation because I can't remember how to do that. I think, let's see, there are many different ways to do this. We would want to do, okay, this is specifications, okay. So we want to say, actually one thing we might want to do is to take the log of those, let's do this, let's take the logarithm of the, of the things, okay, let's do this. Let's say, okay, so let's call this masses, and let's call that log masses. Is log to the base 10, let's say, of the things on line 86. Okay, so let's do this. And now let's just see what happens. Let's just look at the histogram of these. I'm just really surprised that, actually I have a better idea here. Let's do that. Let's log masses. Okay. Oh, that's kind of interesting. Okay, so that's the distribution of the logarithm of the mass of a meteorite. Okay? Okay, so next idea. Let's take that distribution, log masses, and let's say we have a nice little machine learning function that's called find distribution. And let's, I don't know what it's going to do, but let's see what happens here. Let's say we want to get, let's do this. Does not have the data. Okay, that was bad. All right, let's look at this log masses thing. What does it look like? Those look like they're all numbers. That's a bit of a surprise here. Oh, I know what the problem is. I know what the problem is. Oh, very odd. Okay, well, let's just check. Let us go select in line 92, not number q hash. So that's going to find all things. Oh, I see. There are a bunch of elements there that weren't numbers. Okay. So what we want to do from this log masses thing, we'll say log masses is select log masses, comma, number q, and that will then just select the ones that are numbers. Okay? So now I can say, given that, I should be able to say this. Okay, so now this is crunching, trying to find out what it thinks the best distribution that fits. Okay, so it thinks it's a mixture of a normal distribution and a log normal distribution. So remember, this is, let's look at the histogram of the actual logarithm of the masses of the meteorites. There it is. And so now let's compare that with, let's see, that went up to about 6. Let's compare that with a plot of the PDF of the things on line 96, which were those, well, let's just, yeah, the things on line 96 as a function of x from 0 to 6. And so now this will be, that's its guess. That distribution, that's a plot of the distribution that it got. So we should be able to just say, show line 97, see if this works, and line 96. I'm not sure if this is going to work, but we can try it. No, it won't let us do that. Oops, what did I want to do? 98, sorry. The problem is that the scale is way different, because this is in counts rather than probabilities. So what we want to do instead is we want to say, for our histogram, we want to say histogram of log masses, comma, and I think we just have to say probabilities here. Not certain if this is right, but let's see if that's right. No, okay. Oh, how many bins to use? Okay, let's just say automatic set of bins, and let's see. That's not what it likes, okay. There we go. Okay, so now this is showing the probabilities for meteorite sizes rather than the total counts for meteorite sizes. So there's a good chance then that if we say show this together with line 98, that we should get, yeah, there we go. Okay, so it was a lousy fit, but that was its best fit of a distribution for the distribution that it thought was the, we were sort of doing automated science here, trying to find what would be the scientific law that gives the distribution of meteorite sizes. Well, let's try something else from this data. Let's say we get, where was our data set? We'll go down here. Okay, here's the data set. Let's try the year. So it seems to have a field here for the year when well, let's try, we've got rect, lat, rect, long. So let's try that. So lat, long, rect, lat, rect, long. So we could say data set We could say get from the data set all things with rect lat, comma, rect long. Let's see if this works. Let's actually just try, just before I do everything, let's try doing this. No, that didn't work. Okay, let's see, what do I want to do here? No, that's the problem. That's the problem. No? All right, let me see. Now I have to think a little bit more. Let's try taking a look. Okay, so that was the latitude there. So let's try taking from the data set, we want all the elements, and we want to say, the key is, what did I spell it wrong? Oh. Well, so I should listen to what the error messages say. Okay, so there they go. So now if we wanted to, let's say normal of that, and let's select just numbers in there, and let's just, so the first thing we can do here is let's make a histogram of what the latitudes at which the meteorites are falling. That's kind of interesting. So the latitudes, the meteorites tend to fall, where do the meteorites tend to fall? At plus 50 and minus 100. Well, let's try doing the same thing. Let's just, for fun, let's try doing the same thing for longitude. So that means, where is that? That's at the poles, or where is that? Well, let's find out. Okay, so let's try taking this at longitudes also, and let's do the exact same thing for longitudes. So let's do this. Let's do that for longitude, and there we get that. Let's do this. Okay, so this is now the longitudes at which the meteorites are tending to fall. Perhaps what we can do, let's take both latitudes and longitudes and do the obvious thing. Let's take, let's see, what we want to do here is longitude and, let's see, latitude, longitude. So there's longitude, and let's say latitude there, and let's go ahead and transpose that so that we get a pair of those, and let's just see what happens if we just say geolist plot. So this is what this should be doing. Let's see if it works. Horrifying. Okay. Now let's take it apart. Let's actually debug this. Okay, so what we did was we asked for the latitude. Well, first of all, let's see whether I was actually getting the right kind of thing here. So that's the longitudes. I know what the button is. Well, one way to do this is kind of a hacky way to do it, but there's probably a better way to do it. But this should be generating. So what this should be doing is taking those 45,000 meteorite impact points and showing us, I hope, a plot. I'll tell you what. Let's take. No, this should work fine, but we might. I did this in a rather inefficient way. Well, here let's just for fun. Let's just do the first 1,000 of those. First 1,000 for each of these. Maybe I'm doing something else wrong here. But anyway, what I was trying to show you, I think I should live less dangerously, and I should actually try running this piece before I actually put it all together with everything else. So let's just do this for the first 10 meteorite impacts here. Okay, there we go. And now if I transpose these, I should be getting lat long points. Okay, that looks promising. And if I say geolist plot of that, I should be getting, something is very wrong there. What am I, oh, I know what's wrong. Do I know what's wrong? Yes, I think I know what's wrong. What's wrong is that those should have been geopositions. So, let's try, yeah, okay, well, we can obviously get this plot. I'm curious whether we can do a little bit more, well, we could probably do some interesting physics about those meteorite positions, but we could also try doing some completely other API, or I could respond to other kinds of questions. So maybe I'm going to get down a whole, I can go on pursuing this, but I think we're losing people. That's always a sign that I'm yakking on for too long. So what should I do? Do you have questions, or should I you like to suggest things to do here? Or yes, please.
What if you were to plug in something like synesthesia, you were to say, what is the tone for this color? What is the opposite?
I don't know, we can try. I was told, somebody asked me, are you going to need sound for this presentation? And I said, no, I don't think so, but it depends what happens. So, okay. So I can, this may not be too exciting because you may not be able to hear it very well, but you know, we can certainly do something. Okay, so let's take the color red. Let's say we've got, let's get an image of something or other. Let's get a, let's say, image of Mount Everest. I don't know why I'm thinking of that, but let's imagine, actually we probably can do, there's an image of Mount Everest, and now we can do all sorts of color things with that. We can say, you know, what are the dominant colors in that image? Okay, that wasn't very exciting. We can make a chromaticity plot, like a 3D chromaticity plot of that image here, and then we'll get this kind of thing here, showing us where in color space that lies. So now, if we wanted to, we could map color space into well, let's do a 2D chromaticity plot. We can obviously map those positions in color space into something in frequency space. So, for example, let's imagine, just for fun, let us take, let's do this. Let's take some sounds. All right, so I've got a sound at position. Let's do this. This may, again, you may not be able to hear these, which would be really unfortunate for this. But let's just say I've got a sound note. I'm going to have a table of, let's say, 20 sound notes. Okay, now I can make a sound out of those, and we don't hear anything at all. So I'm sorry, this isn't going to be very exciting. But what I was going to do was to take the positions in the color triangle and map those positions into frequencies of notes, for example. Or actually, one thing that just occurred to me, I could use this actual thing as a spectrogram. So then I could actually get a sound whose timbre is the form of. So if I have a sound, it's kind of a clunky thing right now to do this, but I can do this. Let's see. Actually, you know what? I think I've got example data of sound. Now, I probably should get off the subject of sound because we're not going to be able to hear. Great. That is a bad sign. Something about internet connectivity failed. Bad sign. That is odd. Okay, there's something odd about the way this network is configured that isn't allowing it to get to some server of mine. But in any case, hopefully that can be resolved if people are using this later. It doesn't look like a terribly serious problem. But what I was going to do was to pick up some example sound and start making spectrograms from it as a way to see at least the inverse of the operation that I was imagining doing, which is taking positions in the color triangle and turning that into a spectrogram to make a sound. Other, yes, please.
So obviously it has a lot of this permanent things. What about like Russia?
Yeah, I can see that stuff. I mean, I don't know. We can, if we go to, we can go to the Yelp API or something too. But we can, if we go to Wolfram Alpha, for example, and we can say, 10 closest Starbucks to. Now, since it didn't know, actually, this is again not going to know where we are because, let's say, New York City, it's the center of New York City, let's say. So this is, I just said 10 closest Starbucks to the center of New York City. Let's see whether we can compute that in Wolfram Alpha first, and then what's happening here? Okay, so that's great. It gave me the polygon for New York City, but it didn't. Okay, let's do this. Let us find out what we probably want to do. We don't have as so our curated data does not. We have a certain amount of data on chain restaurants and things like this. We don't have the depth of data that something like Yelp has. And if you want to use Yelp, the best thing to do is to go to our service connection system and to go here and to look up the documentation because I don't know how to do this, and to go list of external services, and there's Yelp, and go to the page that's documentation for how to get to Yelp, and let me make it bigger so you can actually see it. So this is showing this is showing an example of how you would connect to Yelp. Now I think with Yelp you need to get a password from them. Let's see. Oh, okay, so this is a connector that's running against their API, and so you need a password from Yelp to be able to actually do this stuff, and you'd also need this error not to be occurring. But anyway, this is so this is showing how you would use the Yelp API to to do some computation, and that was just putting some particular thing on a map. Yeah.
Can you, like, obviously, like you said, guys,
Sure. I mean, as I showed, you can build an API to run in our cloud. You can also connect to whatever API you might have. So if you have a device, we have a very convenient thing called Wolfram Data Drop, which is a way of connecting, for example, a device to so datadrop.wolfram.com. So this is basically the idea is get data from a device accumulated in the cloud, analyze it. So, for example, and you can get the data in from with an API. You can tweet to it. You can send mail to it. You can use various kinds of IFT things like that. Now, what we can do here. So, for example, I could go ahead and I could say data. I could look at the personal data bins that are connected to this particular account that I have here. So, for example, I've got something like this. Okay, so here's a data bin that is based on some sensors that are on my desk. So I could say date list plot of the data that's been accumulated from that data bin, and now it will go through and it will plot the, well, this was from, I don't know when this is, from February or something. This is the pressure as a function of time as measured by a little board that's been sitting next to my computer on my desk at home. And so I could go ahead, actually it would be fun to kind of compare it if I say air pressure data, well, even I could say here, for, let's say, now minus, let's say, this is not going to be comparable, I'd have to do, so I'd say now minus 2 weeks to now. So this is now going to give me a time series of air pressure data for, oh shoot, here was not here, was it? So let's put in something more reasonable here. The air pressure data for New York City, so now I get a time series here, I can make a plot of that time series. I could go and I could say, for example, something like I could, instead of getting a plot there, I could say what's the mean pressure bin. Oops, it has various data points that aren't available, which is kind of odd, but so it goes. And I could, work out a histogram of the air pressure as a function of time in New York City and so on. So that's the kind of thing you do. But adding your own things for devices, the state drop is a good mechanism for doing it. No, the language is also vulnerable on that Raspberry Pi computer. So if you want to connect something directly to a, you actually have a field of voltage and so on, you can plug it into a Raspberry Pi and then have that Raspberry Pi Wolfram engine connect to our cloud, for example, to connect it into the whole system. Yes, please.
Your map projections were very impressive, but what are your 3D options for visualization data? Are they only in spheres? What kind of 3D space do you work with?
Yeah. So we have actually very complete computational geometry capabilities, and which have just been added actually, and we are about to get in another couple of months. We will get even more. But if you do something like you can take something like this. Let's say we've got all sorts of detailed anatomical data about humans. So there's a femur, and I could go ahead and I could probably do some visualization. I could texture map onto this femur or something if I wanted to, or I could say, what's the area of that thing, and it will give me the result. If I want to work out, well, actually, if you didn't see anything in terms of map projections, actually, if you see, if you want to know what map projections, that's the set of map projections that we actually have. We have a really complete set of those kinds of things. And if you want to do, a projection, so there's a geometric transform. Let's see, geometric transformation. Let's see what this does. Yes, so this is a way of doing an arbitrary geometric transformation, so shearing transforms, things like that. I think there's a way to do image geometric, what is it? What is it called? Let me look for one thing here. If I look for Let's see. I'm going to look. Okay. Image transformation looks good. Okay, so this is doing on an image, this is doing an arbitrary function, transforming the image. So for example, that first example there is taking the Mona Lisa and transforming it with a square root. Okay, so you can do that, you can map that onto a 3D object. You can kind of go to town with this type of thing. And I think the mesh stuff that we have in 3D should allow you to do pretty arbitrary deformations and so on, if that's what you want to do. You can also take, yeah, I mean, lots of different things of this kind. The map projections, many of them have a bunch of fancy math that optimizes being able to, because for map projections, we're interested in taking, you know, actual maps of the Earth and so on, and taking all the different features on them and quickly being able to project. And so there's some cleverness often involved in the particular way that those actual map projections are implemented. But with an arbitrary function, I don't think it's particularly. I mean, if I change that square root, I have no idea. Let's change the square root to a cube root, for example, and let's see what happens. Okay, so, and in fact, maybe what we can do, let's just for fun, let's change it to an arbitrary power there, and let's make a manipulate out of this that has a power p ranging from 1 to 10, for example, and let's see what happens to the Mona Lisa in that situation. Let's see what happens here. Okay, so there's the regular Mona Lisa, and now, okay, that's kind of cool. And that's what happens when we've got 10th power or something of it. So, and we could do the same thing. I mean, again, I can texture map this onto a 3D object and so on if I wanted to. All right, maybe one last question. I think we probably have some time. Yes, please. With what was that? Google is primarily a search engine, which is a completely different type of thing. We are mostly dealing with, I mean, I don't know, Google is a big company with 100,000 employees, so I'm sure they do lots of different things. And they do self-driving cars, and I think they were making two-legged robots, but they stopped doing that recently. But maybe they've got a three-legged robot somewhere as well. I mean, but the primary, you know, their primary objective thing is to make a good search engine. And the search engine is really a different kind of thing from what we're doing. That's about taking the, whatever it is, you know, 15 million pages of reasonably interesting content on the web and allowing you to, you know, to rank which things you actually care about on the web. And that's something, I mean, actually, you can use some of the things, we've done some things with that you may see coming out in the next some number of years that address those kinds of issues in an interesting way. But that's a different kind of thing from what we're doing. What we've done with Wolfram Alpha, which is what powers Siri and S-Voice and stuff like that, what we've done there is to try and collect and make computable as much sort of structured data as possible about the world. Whether it's, you know, I mean, I could take, I don't know, let's take a random piece of data. Let's take something like, let's do this. Let's say, you know, I mean, if I say something like this, I say, you know, I'm just making up a different thing, but let's say something like Earth, word translation of Earth, you know, translate that into as many languages as possible, whatever it is, right? So all kinds of weird things here. You know, what we're trying to do is to make a lot of data that is computable and interoperable so that we can actually run it in a language and compute things from it. That's really quite different from what, you know, when you search the web, what you get back from searching the web is a link. And maybe you can import that link and do things with it. I mean, for example, when I did that web image search, I was using somebody else's, might even have been the Google API, to do that search. And what it was doing was bringing back there, you know, a bunch of random images from the web. So it's not bringing back structured things that you can then compute with. So that's kind of and you know, depending on what you're interested in doing, if you're interested in building a lot of stuff on the top of, you know, on the basis of data, then you need some data that's been made computable. If you're interested in finding some needle in the giant haystack of the web, then you need a search engine. And that's kind of the difference of approaches there, I think. Yeah.
actually curious about the types of things you can learn and represent. So, given that as the textual image, could I get something like an image and then ask the question, like, is it cool, this image? Is it going to check it and then be able to understand that this is cool? Things along that line.
Well, so there are different kinds of things. So you know, we have actually coming out in the next couple of months a very, we've been kind of surfing the wave of what's been happening in kind of the machine learning world. And what we have in what exists here is kind of the pretty much absolutely, a little bit beyond state of the art of things that can be done as of about 6 months ago. What we will have coming out is something that's kind of rather beyond the state of the art of what's sort of supposed to be possible now. What's here now, if you had, for example, you know, if I take a bunch of pictures, I mean, a very simple-minded version of this. Let's just show you how to do some image classification. So let's say I've got, I think I had an example here. Let's try this. Let's try, here's a good trivial example, okay? So let us see, so this is a training set, a tiny training set, right? Where we've got a bunch of images where we say some of them are night and some of them are day, okay? So I'm going to use that as a training set, and I'm going to say, make a classifier based on, okay, so it just used logistic regression in this case. It's a small training set, it's not going to do anything terribly exciting. But now I've got a function, day-night, that I can feed any image I want to. So for example, I could feed it, let's pick some image that I had here. Well, let's feed it the image of the otter, for example, here. And let's go ahead and, we'll be back down here. Wrong way here. Okay, so let's feed it that image of an otter, and it'll probably tell us, okay, it'll tell us it's day, right? So that's a sort of trivial thing given an existing training set. If you're asking, do we have an already trained system that can tell you a story about a picture, the answer is that we do not yet have a released such object. But we do have, you know, again, we have an image identifier that will tell you for pretty well. Let's see what it thinks that is. That hopefully, what is that? What the heck is that? That's embarrassing. Well, it looks, maybe it looks underwater here. It uses anyway. So the answer is that one of the challenges there is how do you represent? I mean, this is a long story. I mean, how you represent things in the world. We have a great way to represent. I mean, if I have something like, let's say, you know, chocolate, for example. Okay, I have a pretty good way to represent, you know, foods with chocolate, and I can say something like, what could I say? I could say, I don't know. Let's see what this works. Is that going to work? No. What is it going to work? It's going to work here. Let's see. I could say. This may generate a huge long thing, but so you know, I could ask it all kinds of properties of chocolate. But if I want to represent some statement like I want a piece of chocolate, that's a different and separate thing, and wait for the future. Wolfram language parallel configuration can say, you know, evaluate. I mean, I could just say something like, you know, parallel table, some trivial thing like, you know, $process ID or something. And if you watch carefully, this computer probably has 4 cores, so it will start up 4 kernels and run and distribute that trivial computation across 4 kernels. We've done a lot with natural language understanding. We've done less with things like, you know, if I say something like text structure, this is a nice day. This should, wake up, okay. There we go. So that should give the parse tree for that sentence, and I could probably say dependence. Let's see, what do I want to say? I want to say constituent tree here, and now I can get constituent graphs. Now I should be able to get. Okay, so there's the graph of that. I can pick this up, and if I wanted to, I could do. Well, let's do something. Let's do Wikipedia data of NASA So this will get us the, oh, come on. Okay, that's going to get us the Wikipedia page for NASA. You know, I could, if I wanted to, I could just say something like word cloud that. Let's delete the stop words because it will not be so interesting to see it with the stop words. So that will just give us this word cloud. Okay, great. Space is big for NASA. We kind of knew that. Now what I could do is I could say, just for, let's live dangerously here, and let's say, let's take this and let's say text structure of, let's say text sentences of that, comma 3, for example, and that should give me the first 3 sentences of that thing, and now I could say text structure of, let's see, that, and then constituent graph of that. And so what that should do, okay, there we go. So there's the, there are the graphs for those 3 sentences, and just to really live dangerously, let me just for fun, let's see what happens if I do, okay, there we go. There's the graphs of those things. Let's get something like the community graphs for each of those graphs. So let's see what happens if I do that. Let's try this. Am I going to regret this? Oh, there we go. That's kind of fun. Okay, so that's the sort of community graph of the parse tree of that English sentence. All right, thanks a lot.